Welcome to this lesson, viewers. Today we are going to have a discussion on the topic length, area and volume, and we are going to discuss the following. We have dimensions of length, area and volume, polygons, cubes and cuboids, we have prisms and pyramids, we have cylinders, cones and spheres, then finally lengths, areas and volumes of similar shapes. Now, starting with dimensions of length, area and volume, we can say that length is represented by a line, and that means it is one dimension because we can only have the length. That is what we can measure. It is stated in the following units: millimeters, centimeters, meters, kilometers, inch and foot. Number 2 is on area, and area is represented by a plane because it is two-dimension. Two-dimension means we can find the area by having length times length, and area can be measured in the following units. We have square millimeters, square centimeters, square meters. It can also be given in hectares, square kilometers, square inch and square foot. Number 3 is on volume, and volume can be represented by using a cube or a cuboid. That means it is 3-dimension because to find volume we will have it as length times length times length. That is if it is a cube, or length times width times height if it is a cuboid, and some other figures. Now, volume is stated in the following units: cubic millimeter, we have cubic centimeter, cubic meters, cubic inch and cubic foot. Our second subtopic is on polygons, and we are going to look at various kinds of polygons, starting with rectangles. And the perimeter of a rectangle with length L and width W can be written as 2L, because we are basing our formula from the diagram, which is a rectangle of length L and width W. Now the perimeter will be 2, because the lengths are 2, so we shall have 2L, where L is the length, plus 2W, where W is the width. And we can simplify our perimeter to be 2 into length plus width. Now, the area of a rectangle is given as area is equal to length times width, and that is shortened as length times, that is LW, meaning length times width. Number 2 is on squares. When the length and the width of a rectangle are equal, we call it a square. Therefore, a square is just a special type of rectangle. And now the perimeter of a square with length L is given as 4L. And from the diagram, it is a square of length L, and all the sides are equal. And so, because the perimeter is the distance all around a given figure, we will take length plus length plus length plus length. So that one gives us 4L, or 4 times length. What about the area of a square? The area of a square is given as area is length square, or length times length. Now, shapes made from rectangles, how can we find the area of the shaded shape? We have here 2 rectangular models. the bigger rectangle is of length 11 centimeters and its width is 9 centimeters. The other smaller rectangle, which is fixed inside the bigger one, is of length 6 centimeters and width 4 centimeters. Now we are supposed to find the area of the shaded shape. So we can think of this shape as being made of one rectangle cut out of another rectangle. And so we can label the rectangles as A and B. And now that will make us, or will be very easy to find the area of rectangle A. Then we find the area of rectangle B, and then we'll be able to subtract. Now, area of rectangle A is 9 times 11 because it is length times width, that is 99 square centimeters. Then area of rectangle B is 4 times 6, that is 24 square centimeters. And now the area of the shaded part we are going to subtract, and that is 99 minus 24, giving us 75 square centimeters. Now let's move to the area of a triangle, and we have a diagram here showing a triangle of base B and height h. Now the area of a triangle with base B and perpendicular height h is given by, we have a half base times height. That is the formula for finding the area of a triangle of base, given the base and the height. Now, any side of triangle can be taken as the base as long as the height is perpendicular to it. As you can see in the first diagram, we have the base being perpendicular to the height, and the second diagram the same way. Now, some assignment: find the area of the triangle drawn below. So the base of this triangle is 15 centimeters, or just 15 units. Its height is 10 units, and we are required to find the area of this triangle. And here the best and simplest formula here is a half base height. So I'm not going to give you the answer in this case, but how I hope that you do you attempt this question for better understanding of the previous concept. Now, suppose that instead of the height of a triangle, we are given the base, one of the sides, and the included angle. Then we can use trigonometry to find the area of the triangle. You realize that we have been given the base, and we have all the sides, and we have an included angle in this triangle. So this one we cannot apply a half base height, but we can use a half AB sine of theta. We can use a half AB sine of theta because the two sides are given, that is A and B, and the included angle is at point C. So area of triangle ABC can be given by a half AB sine of C. That can work for this triangle. Now let's move to area of a parallelogram. The area of any parallelogram can be found using the formula. We have the base times perpendicular height, that is BH, and we have an example of a parallelogram drawn below with the base and perpendicular height. And so, using the symbols, area can be given by BH, where B is the base and H is the perpendicular height of the parallelogram. Let's have an example on this. What is the area of this parallelogram? The diagram given below is a parallelogram of sides 7 centimeters and 4.9 centimeter, and of height 4.5 centimeter. And because we have that area of a parallelogram is given by base times height, now we are going to use the height, which is 4.5 centimeters, and not the other side, which is 4.9. So you ignore that other length, because the height of the parallelogram given below is 4.5 centimeters. And now the area will be 31.5 square centimeters. Now, moving to the area of a trapezium, we have that the area of any trapezium can be found using the formula. Area of a trapezium is given by a half into sum of parallel sides times height. So the diagram below is a trapezium with the two parallel sides labeled A and B, and of height H, that is the perpendicular height. And now we have that area of a trapezium can be given by a half into A plus B H. This can be simply put as half H into A plus B as the area of a trapezium. That is the formula. Now, an example. What is the area of this trapezium? So the diagram below is a trapezium of height 9 meters, and the shortest length of its parallel sides is 6 meters. The other longest one is 14 meters. And with the formula, of course, for you to find the area of any given polygon in this case, then you must start by stating the formula. Then you substitute into the formula, and then finally you get the answer. Now, area of a trapezium, we have that it is a half H into A plus B. And if we can substitute, then we have a half into 20 times 9, which is the height. And that gives us the area to be 90 square meters. Another example on trapezium. We have been given a trapezium of height 12 meters and two parallel sides 9 meters and 4 meters. So, substituting into the formula to find the area, we have a half into 13 times 12. Then that gets us 78 square meters. Let's have assignment. Find the area of the trapezium drawn below. We have a trapezium of height 10 centimeters. The length of the two parallel sides of this trapezium are 15 centimeter and 10 centimeter. Now you can use the formula and substitute, then finally find the area. It is good to take assignment and be able to do them to be able to have enough understanding of the concept that we have just gone through. So moving to another subtopic on cubes and cuboids, we find out that a cuboid is a three-dimensional shape with edges of different lengths, and all of its faces are rectangular or square. So the diagram here is a cuboid, and now we want to look at some of the features of a cuboid. So you find out that a cuboid has faces, like the one shown here, that is the top face. A cuboid has edges. The one shown here is an edge, and a cuboid has vertices. The one shown here is a vertex of a cuboid. So, figuratively, a cuboid has 6 faces. You can count them. We have the top face, bottom, the side and back faces, and the side faces. Then the number of edges are 12. You can as well do the counting. And lastly, the number of vertices are 8. So all that is on cuboid. Now let's move to a cube. A cube is a special type of a cuboid with edges of equal length. All of its faces are square. So let's have an example here. Suppose we have a cuboid of length 5 centimeter, width 4 centimeter, and height 3 centimeters. What is the total length around the edges? So imagine the cuboid as a hollow wire frame. So this cuboid has the length of 5 centimeter. We have 4 centimeter on its width and 3 centimeters on its height. Now we have that cuboid has 12 edges. That means 4 edges are 5 centimeters long. Again, we have 4 edges are 4 centimeters long. And again, we have 4 edges are 3 centimeters long. So that means the total length around the edges are, we have 5 times 4 on the length. Then on the width, we have 4 times 4. Then on the height, we have 4 times 3. So that gives us a total of 48 centimeters. And now we have that to find the length around the edges of a cuboid of length L, width W, and height H, we can use the formula. The length around the edges to be given by 4L, that is 4 times length, plus 4W, that is 4 times width, times 4H, that is 4 times the length of the height. And or you can say by doing the simplification, 4 into length plus width times height. So to find the length around the edges of a cube of length L, we can use the formula, that is 12L. Now, surface area of a cuboid. To find the surface area of a cuboid, we calculate the total area of all of the faces. Okay, so we have that a cuboid has 6 faces. So the top and the bottom of the cuboid have the same area. So those are 2 faces. So we have the side faces, no, the front and the back faces of the cuboid, which have also the same area. And again, we have the side faces, which is the left hand side and the right hand side of the cuboid, having the same area. Yeah, so the formula for finding the surface area of a cuboid, we can find the formula for the surface area of a cuboid as follows. So we have a cuboid below of length, height, and width. So we can find the surface area of the top and bottom faces. that is 2 times length times width, because length times width is the area of one face, but there are two faces, so it is 2LW. As well, we have the front and back faces, so we add to the previous area, that is 2 times height times width, another area for the front and back. Then lastly, the left and right hand side faces. So that means we are going to add it to the previous areas. And now we can sum up the surface area of a cuboid as 2 length times width plus 2 height times width plus 2 length times height. And now, moving to surface area of a cube. So let's be guided by this example. How can we find the surface area of a cube of length L? And now, we have that all 6 faces of a cube have the same area. That means the area of each face is length times length, given as length square. And therefore, the surface area of a cube is 6L square. That is 6 faces times the length of each face. Now, let's move to a volume of a cuboid. And now we have that an example of a cuboid given below. So this cuboid is made of interlocking cubes. And so you may be asking yourself that the number of cubes that is contained in this cuboid. So we can work out this by dividing the cuboid into layers. So the number of cubes in each layer can be found by multiplying the number of cubes along the length by the number of cubes along the width. And so this means along the length we have 3. So we have 3 times 4. That will give us 12 cubes in each layer. And therefore, we find out that there are 3 layers altogether. So the total number of cubes in the cuboid, we have that 3 times 12, that gives us 36 cubes. Now, we can find the volume of a cuboid by multiplying the area of the base by the height. So we have the area of the base to be length times width. So the volume of a cuboid is length times width times height as the formula for finding the volume of a cuboid, length times width times height. So how can we find the volume of a cube of length L? So we have that the length, width and height of a cube are the same. Therefore, this means that the volume of a cube is length of one edge, then cube, or raised to power 3. That gives us length cubed, or length raised to power 3. Now, let's take an example. What is the volume of this 3-dimensional shape? So we can think of this shape as two cuboids joined together. And so now, as you can see, our initial diagram was this. And now, we have two cuboids from this diagram. And because we want the volume of the whole figure, then we will find the volume of the green cuboid. That is length times width times height, giving us 54 cubic centimeter. And again, the volume of the blue cuboid, giving us 3 times 2 times 2. That is 12 cubic centimeters. Cubic centimeters. And now we add the volumes to find the total volume of the figure. That is 54 plus 12, giving 66 cubic centimeters. Now let's move to prisms and pyramids. And we have that a prism is a three-dimensional shape that has a constant cross-section along its length. For example, this hexagonal prism shown below has the same hexagonal cross-section throughout its length, as you can see, from the front part to the cross-sectional face at the back. It is all the same. So this is called hexagonal prism because its cross-section is a hexagon. So hexagon is a polygon of sides 6 or of 6 sides. Okay, now we have that the volume of a prism is found by multiplying the area of its cross-section by its length, or by its height if it is standing on its cross-section. So in the diagram below we have a triangular prism because the cross-section is a triangle. That is the first diagram. And now the volume of this prism can be given by the cross-sectional area times length. Same to the second diagram because all of them are prisms. Now let's have an example. What is the volume of this triangular prism? And now from the diagram you can tell that the cross-section is a triangle because the base is 5 centimeters and height is 4 centimeters and the length is 7.2 centimeters. And now area of cross-section is, because it is a triangle, then we have a half times 5 times 4, giving us 10 square centimeters. And now volume of this prism will be 10 times 7.2, giving us 72 cubic centimeters. Example number 2, find the volume of this prism. So we are going to find the cross-sectional area, which is the area of the bigger face minus area of the smaller face, and that will give us 7 times 12 minus into bracket 4 times 3, and that will give us an area of 72 square meters. Now finding the volume of this prism, we have the cross-sectional area times length, or Now we have 72 times 5, we have 360 cubic meters. Let's now move to surface area of a prism. So here is a net of a triangular prism. So we are to find the surface area of this prism. So we can work out the area of each face and write it in the diagram of the net. So the area of the cross-sectional part is 60 square centimeters, that is each. And now if you calculate the area of the rectangular part, you will get 260 square centimeters on each face, with the base being 200 square centimeters. Now the total surface area, we are going to add all the areas given that we have got from each face. And now we have that the surface area of the triangular prism is 840 square centimeters. Now number 2, pyramids. We find out that a pyramid is a three-dimensional shape whose base is usually a polygon, but can also be a shape with curved edges. The faces rising up from the base meet at a common vertex or apex. The most common pyramids are, we have examples of various pyramids. We have a tetrahedron or triangular pyramid. We have square based pyramid, and we have a cone. Now the volume of a pyramid is found by multiplying the area of its base by its perpendicular height and dividing by 3. So we have the base of this pyramid, then we have the perpendicular edge, and then we have the slanting height of the pyramid. So to find the volume of this pyramid, we have that a third times area of the base, that is base area, times height, will give us the volume of this pyramid. This is simplified as a third AH. Now let's have an example here. What is the volume of this rectangular based pyramid? Now we are going to substitute into the formula now that we know the formula. So area of the base is 15 square centimeters. Then the volume of this pyramid will be a third times 15 times 8, giving us 40 cubic centimeters. Let's now move to the surface area of a pyramid. And now from this diagram, we can find the surface area of this pyramid. So area of each face, having that it is a triangle, so we are going to use a half base height because we have been given the base and the height. So area of each base is 15.6 square centimeters, and you realize that there are 4 faces. So surface area of this pyramid will be 4 times 15.6, and that gives us 62.4 square centimeters. Now let's move to cylinders, cones and spheres. And now starting with the volume of a cylinder, we have that by definition a cylinder is a special type of prism with a circular cross-section as shown in the diagram below. So we have this a cylinder of height h, and the circular base is of radius r, and now the volume of a cylinder is given by that is area of the circular base times height, shortened as pi r squared h. Now the surface area of a cylinder, so to find the volume of the surface area, to find the formula for the surface area of a cylinder, we can draw its net. And now we can also find the width of the curved surface of this cylinder. So the width of the curved surface is equal to the circumference of the circular base, that is 2 pi r. And now area of the curved surface will be, of course, the length times a width, whereby on the length we have 2 pi r, on the width we have h. So area of the curved surface is 2 pi r h, and area of two circular faces are 2 times pi r squared, because there are two circles at the ends. That is if it is a closed cylinder. So surface area of a cylinder, we have 2 pi r h plus 2 pi r squared. Or this can be simplified as 2 pi r into h plus r. Moving to the volume of a cone, so we have that a cone is a special type of pyramid with a circular base, and the volume of a pyramid can be found by multiplying the area of the base by the height and dividing by 3. So we have the volume of a cone given by a third times area of the circular base times height, that is a third pi r squared h. Then moving to the volume and surface area of a sphere, so we have that a sphere is a three-dimensional shape whose surface is always the same distance from the center. This fixed distance is the radius of the sphere. And now, for the sphere of radius r, the volume is 4 over 3 pi r cubed, and its surface area 4 pi r squared. Now, as we end to close our lesson, let's handle the last subtopic on the length, areas, and volumes of similar shapes. So we start with lengths in similar shape, and we have that when a shape is enlarged, every length in the shape is multiplied by a given scale factor, and this is what we call the linear scale factor. So suppose we enlarge a cube with side length 2 cm by a scale factor of 3, is shown in the diagram below. A smaller cube is of 2 cm, then the linear scale factor is 3, then it means the other length will be 6 cm. You multiply the length times the scale factor. So this length is enlarged by a scale factor of 3, and we have 6 centimeters. Let's now look at the areas in similar aspect. Compare the area of one face of the original cube to the area of one face of the enlarged cube. So we are going to enlarge this. So this face, which is initially it was the length, the side is 2 centimeters, but because it is a cube, then all its sides are 2 centimeters. So it means the area of one face is 4 square centimeters, and after an enlargement, the area of one face of the other enlarged cube is 6 times 6, that is 36 square centimeters. So it is area being enlarged by a scale factor of 9. So the area is enlarged by a scale factor of 3 square. On the volume, if you compare the volume of the original cube and the volume of the enlarged cube, so we have the volume of the smaller cube is 2 times 2 times 2, giving us 8 cubic centimeter. The volume of the enlarged cube is now 216 cubic centimeter. That is after being enlarged by a scale factor of 27. So the volume is enlarged by a scale factor of 3 cubed. And now in summary, if an object is enlarged by a scale factor of k, then its area or surface area is enlarged by a scale factor of k squared. So you just take that length, then you square it. You'll get... Okay. So if an object is enlarged by a scale factor of k, then its volume is enlarged by a scale factor of k cubed. So that means if the length is k, then the scale factor will be, if it is volume, scale factor will be k cubed. And again, if the length is k and you are finding the area of the enlarged object, then you use a scale factor of k squared.